So good afternoon and sorry for the delay. So today I will start from the point where we have left in the last lecture, in the 10th lecture. Should I go? Okay. Okay. So we were the outline in this talk will be like I will continue in the advancement in DAC technique. And then I will talk about the Bevelled diamond anvils in detail. I will talk about the recent advancement in the diamond anvil cell techniques like double stage DACs, toroidal DACs, and what are the recent developments in the pressure scale calibration. And if time permits, I will talk in the diamond anvil Raman gauge in multi-megabar region and techniques and tools for achieving high megabar. And in further lectures, I will talk in the high pressure, high temperature techniques, importance and their examples. So here we were in the last talk, we were saying that one can study the high pressure samples inside the diamond anvil cell using either the flat type of diamond anvils, or if you want to go to the further higher pressure, what you do really is since pressure is force per unit area, so you try to reduce the area to go to the higher and higher pressure, because there is a limit, ultimate limit to the force. So you can't increase force beyond a limit given the design of the cell and given the pressure, given the force applying mechanism. So you start decreasing the area. So it is not something like you just go on decreasing the area and the pressure will increase more and more. Because a limit comes where you can't increase the pressure beyond 100 GPa, even if you whatsoever area you decrease. So then comes the tricks of other things, like you start diamonds beveling. So beveling means now you have a culet, large culet from here to here, but you give an angle of this small culet. So you have a angle between this small culet area and then this final this large bigger size culet A and B. So this angle, depending on this angle, people have optimized this angle to be around 7 to 8 degrees, and one can have single bevel like only one small culet, and instead one can have two culets, like two bevels, like one small culet A, which is on the larger culet B, and it is further on the unpolished larger culet C. So basically you have this larger culet of the size C, like 400 or 450 micron area, and then you start polishing it in such a way that angle between B and C is alpha, and then you can further polish it with the further smaller area, and such that the angle between A and B is again another angle alpha. So these are called double bevel anvils. So what are the advantages of these bevel anvils is, like you not only achieve the higher and higher pressures, they also support you from avoiding the pinching of gasket. So by beveling, you are able to avoid the pinching of diamond into the gasket. Otherwise, if you don't bevel, what happens that diamond pinches into the gasket at the higher pressures. And not only that, diamond also suffers ring crack and different kind of cracks if they are not beveled. That is because of distribution of shear stress on the culet edge, as I have shown you in the last lecture. So beveling helps you distributing the shear stress at the culet edge as well as to avoid the pinching of the gasket. So this is one typical example of a Drucker cut diamond mounted on top of tungsten carbide sheet. So if you want to achieve higher and higher pressures, like pressures in the range of 100 GPa or 200 GPa, it is not only the diamond, design of everything matters here, like design of your backing plates or backing seats where the diamond seats, then design of your mechanical design of your and mechanical design of your cells actually. All these things matter. Like for this kind of cells, there is a very fine tolerance between the piston and cylinder pieces of the anvil. So here, this figure shows you the different pressure distributions across the different pressure ranges. Like you see here, around 170 GPa, this is the y-axis shows pressure and x-axis shows distance from the anvil center to the anvil. Like this is at the center of the anvil, and this has been shown up to plus minus 150, like 300 micron. And this has a bevel of 8 degree, and the inner culate diameter used here is around 50 micron. So with this, you see that starting from 170 GPa, how the pressure distribution changes as you increase the pressure. So with at the 170 GPa, the pressure distribution is finely symmetric. But as you go to higher pressure like 240 GPa, the pressure distribution becomes asymmetric across your culate size. And of course, at higher and higher pressure, like at 400 GPa, you see how asymmetric the pressure distribution becomes outside your gasket age actually. And this figure again shows the same diagram in a zoomed view. So you see here, it has been zoomed from minus 15 to 15, like 30 micron culate size, like 30 micron anvil center. So you see the typical.
Ajay, just one comment.
Yes,
you can take help from the person sitting here to activate your indicator, because I can't see your indicator.
Okay. So now I think it is visible, the red thing. Yeah, now I think it is visible. So you see here in the down one in the magenta graph that 170 GPa, and so more or less in the 30 micron region of the sample, like minus 15 to 15, the pressure distribution is kind of same in all the pressure ranges. And this graph shows the pressure thickness distribution, like thickness of the gasket as you increase the higher and higher pressure. So you see here that at 1 atmosphere, the thickness of the gasket is 5 micron. So to achieve these kind of pressures, the indented thickness of the gasket to start with itself is 5 micron. You can understand. So you have to make the hole in the indented gasket with 5 micron thickness. And as you increase the pressure, like you see here, as you increase the pressure, the thickness also, like you see that there is a bulging kind of effect in the higher pressure range. And this can be seen in a more elucid way in this diagram, where it has been taken like minus 20 to 20 range, 40 micron range. So you can see that starting from 170 to 400 GPa, your thickness, gasket thickness comes down, like at the ambient it was 5 micron, and at 400 GPa, it comes down to almost 1.5 micron. And you see the pinching here, pinching at the edges kind of thing. So you see at the around minus 10 and 10 edges, there is a pinching again in the gasket. And this cartoon shows you typical bulging effect, like at the higher pressures, like the megabar region or beyond megabar region, what happens, like your diamond itself start topping actually. So this figure is in the minus 150 to 150 range. And like if you zoom it, you see the bulging of the diamonds. So diamond behave like a cup actually. And this is also called cupping or lensing effect in the anvil at megabar pressure. And this cupping effects actually causes many problems, especially in the optical measurements. So in the next slide, I am going to talk about what are the recent advances in diamond anvil cell technique. Like with use of this diamond anvil cell techniques, you can really do many experiments at megabar pressures, whether at synchrotron or lab-based experiments. You can really do transport measurements like electrical resistance measurement or magnetic measurement at megabar pressures. So first advancement I will talk, like as I had talked in the large volume presses also or multi-envelope presses also, the use of double stage multi-envelope use of double stage. Like in the multi-envelope presses, in addition to the tungsten carbide anvil, we also use sintered diamond anvil and as a double stage. Here in the diamond anvil cell, also that concept has been used and people have used double stage diamond anvil cells. So they have discovered or invented this double stage diamond anvil cell, and using this double stage diamond anvil cell, it has been shown that you can really achieve static pressure in the range of terapascals. Terapascals means almost in the range of thousands of GPa, which are really till now you can't even visualize or you can't even think that using the static, using the diamond anvil cell, which fits into your palm or which fits into your hand, you can study the materials at the thousands GPa of range. So in the 2016, this Dubrovensky group, they have done marvelous experiments and marvelous discovery based on the nano diamonds. So here, what they have used in the double stage, they have used this especially fabricated nano diamonds of 20 micron size. So how they have synthesized or fabricated these nano diamonds? So they have used glassy carbon as precursor material, and then using this glassy carbon, using the multi-envelope apparatuses, they have synthesized diamonds with help of this glassy nanocrystalline diamond with help of this glassy carbons at high pressure and high temperature. So you see what is the application of high pressure and high temperature as well as these multi-anvil apparatuses. Like you can really synthesize larger size like 20 micron size balls, which are optically transparent micro balls as claimed by Dubrovensky, and they are nanocrystalline diamond. They are not nano polycrystalline diamonds. They are not NPDs. They are nanocrystalline diamonds, NCDs. And these are synthesized at 18 GPa and 2000 degrees Celsius. And these are the optical characterization of these nanocrystalline diamonds. So you see here at 1335 or 1335 centimeter inverse, we see the first order diamond peak of single crystal diamond, while this is the diamond peak of nanocrystalline diamond, very broad, and it comes centered around 1500 centimeter inverse. And in this second pattern, you see there is still signature of polycrystalline, there is still signature of single crystal or polycrystalline diamond, but so they have used this Raman tool, or they have used the Raman spectroscopy to check the quality of this synthesized nanocrystalline diamonds. So they have used only those nanocrystalline diamonds which does not have the single crystal or polycrystalline signature. So they have used only this kind of spheres which have only this broader peak corresponding to the nanocrystalline diamond. So what are the advantages or what are the special properties of these nanocrystalline diamonds because of which one is able to go to the very high pressures in the range of terapascal pressures using the double stage diamond anvil cell, is because they have very high yield strength, that is 460 gigapascal. even the yield distance of diamond is less than this. And not only that, they have very high hardness, which I explained to you all these parameters, hardness and yield strength. They have very strain dependent elastic properties. So these nanocrystalline diamonds, they have outstanding mechanical properties. In addition, they have thermal stability, quite good wear resistance, fracture toughness, and not only that, they are structurally isotropic and homogeneous. And in addition, because this is made up of carbon, like glassy carbon, so this is low Z materials consisting carbon only. So they are extremely useful for X-ray diffraction, at least X-ray diffraction studies at synchrotrons. So advantage here is
What happened? Some problem?
Some camera issue is there.
Ajay, while he sets this, I have a question. You hearing? I said
Yeah.
Okay, start.
Yeah. So the advantage here is that first stage diamond anvils remain intact. So unlike the beveled diamond anvils or unlike the normal flat diamond anvils, where if you want to go to the very high pressures, your diamonds are bound to go, like diamonds are bound to break. Like once you release the diamonds, you will not get those diamonds actually. They break apart. But in these cases, your first stage diamond anvils remain intact in contrast to beveled diamond anvils. And using these nano double stage diamond anvil cells, you can achieve ultra high static pressures in the range of 1 terapascal. So this bulk modulus they have determined for these nanocrystalline diamonds to be 482 GPa, and bulk modulus of, like if you compare the bulk modulus of single crystal diamond or nano polycrystalline diamonds, that is 442 GPa. So this has higher bulk modulus than even the single crystal diamond. And of course, yield strength of single crystal diamond is only 82 GPa, while yield strength of these nanocrystalline diamonds are almost 460 GPa. Not only that, so why these nanocrystalline diamonds, they have this kind of property? So this is basically because of their special microstructure. So these nanocrystalline diamonds consists of diamond nanograins with sizes ranging from 2 to 15 nanometer in diameter. And then these nanograins are entangled with each other, and that causes the higher bulk modulus and this very high yield strength. Next. So what they have done really, like this shows, they have used the rhenium gasket and sample, and this is their polycrystalline nano diamond. So using in one of their experiments, they have used only one piece of nanocrystalline diamond and used the rhenium gasket and determined the equation of state of rhenium gasket up to 600 GPa. But in recent advancements, what they have done, they have made special gaskets for this, and in those gaskets they have basically stick these nanocrystalline spherical shaped nanocrystalline diamonds on both sides of this gasket, and then they have sandwiched this assembly of gasket and nanocrystalline these balls in the primary anvils. And using this double stage, they have determined the equation of state of gold up to almost 1065 GPa. And you see here, this is the refinement of diffraction pattern of gold at 1065 GPa using the double stage diamond anvil cell technique, using the synchrotron monochromatic X-rays of 0.31 angstrom. So they determined this lattice parameter of gold to be 3.174 angstrom at 1065 GPa, and this paper was published in Science Advance. So in the next slide, I will show what kind of intricacies or what kind of involved work is involved in preparation of this kind of cells and this kind of gaskets. So you see here, I have given 4 steps: step 1, step 2, step 3, and step 4. So in step 1, they have especially fabricated the internal gasket in this double stage diamond anvil cell to go into the terapascal region. So what they do, they take a larger size anvil of 250 micron and take a metallic gasket, especially rhenium as the metallic gasket, because rhenium has high yield strength in the megabar region than the tungsten, and tungsten has brittleness, so people prefer to use rhenium gaskets as metal gaskets in the high pressure range. So in the first step, they have taken a 200 micron culate, a 250 micron culate, and a gasket with thickness, initial thickness of 200 micron, and indented it so that the thickness of the gasket of indented portion becomes 25 micron. So using this 250 micron culate, in the first step, they indent it from 200 micron to 25 micron. So now after first step, the thickness of the gasket is 25 micron, indented portion gasket. Now they take this gasket, indented gasket of 25 micron thickness, and use it in the second step with another anvil of 100 micron culate. So with this 100 micron culate, they again indent this 25 micron thickness gasket, and in the second indentation, they go to the thickness of around nearly 3 micron. You can understand how involved work is in going from 25 micron to 3 micron. It takes really very, very careful and many steps to go from step 1 to step 2. And once you have a 3 micron gasket, you drill a hole inside this 3 micron, and that drilling again is a special kind of drilling, like you can't use your hand or mechanical drilling. These are used with the pulse laser, with the very fine pulse beam, with the laser drilling, and you make a hole of the order of 3 to 5 micron in the 3 micron thickness. So now you have a cylinder of 3 micron diameter and 3 micron thickness. So what they have done is now, in this sample chamber, using the micro manipulator. Here I have shown a micro manipulator because now to handle these samples of the size of 1 micron, 3 micron, 2 micron, it is very, very difficult, and it requires lots of practice to do by hand. So you use micro manipulators. Like using micro manipulator machines, you can really maneuver the 3 micron sample on top of your sample chamber. And then once you assemble this gasket with the sample chamber, now you assemble the semi-balls, which they have synthesized using the multi-anvil apparatuses and quality checked and done everything. Those nano diamonds, nanocrystalline diamonds, they stick it on both sides of this sample chamber on the sample. And in the step 4, they stick it, and then this whole thing is sandwiched between the primary anvil of the larger size, like 100 micron culate size, with the bevel end. and thus they are able to achieve very high pressures, and with this only they have done the equation of state of gold up to 1065 GPa using the ESRF synchrotron source. So these kind of experiments are really very challenging, but they give the proof of technique, they demonstrate, they are authoritative that yes, using static high pressure also, you can do experiments in the range of terapascals. So all said done, there are some limitations also of this double stage diamond anvil cell. Of course, these kind of anvil cells are not for the common use. So although it has been demonstrated by Dubrowenskia that this double stage diamond anvil cell can be fabricated using uniquely synthesized nanocrystalline diamonds of a spherical shape, and the same can be reproducibly applied to reach 500 GPa, in some cases even terapascal length. However, the HPHT synthesis event, the first step of synthesis of nanocrystalline diamond from the glassy carbon material, is itself very tedious and demanding task, and it is still not reproducible by any other group. In fact, T. Sakai et al., they have published one paper in the high pressure research and have shown that in their recent publication that the synthesis of NCDs, like these nanocrystalline diamonds, they are not able to do it. And whatever they have synthesized, nanocrystalline diamonds have various shapes and sizes and of varying quality. So they have also reported some reservations with the range of pressure achieved based on the equation of state of rhenium itself and gold. So not only that, in these kind of experiments, you really require nano-size X-ray beams to probe the samples at such high pressure using double-stage diamond anvil cells. And not only that, in some cases, micro-cracking of second stage anvil is also observed by Sakai et al. So I don't know whether they were not able to synthesize these spheres, nanocrystalline diamond spherical balls of the same quality as the synthesized by Dubrowenskia et al. So how to overcome these limitations and still go for pressures in the range of 500 GPa and still make people available this kind of pressure routinely? So the answer is toroidal diamond anvil cell, t-DAC, which is again a breakthrough in diamond anvil cell technology. And Agnes Diwale et al. In the Mohammed Misor group, what they did, so they have married the concepts of toroid anvil press and DAC. So I have already explained you that in the Dr. Himanshu might have explained that what the toroid anvil is and what are the advantages in case of large volume press of having toroid shape of large volume press. So this is a typical toroid anvil which is used in large volume presses. So you see here, so toroid type of gasket. So what happens in the center here, you have the sample and there are two locking points here. So in any case, in the toroid anvil, you have the gasket intact, and you don't like the gasket failure is avoided in case of toroid anvil because of this special toroidal shape. So in this toroid diamond anvil cell, we have married the concept of toroid anvil and diamond anvil. So what they are doing, that they are cleverly making this toroid shape on top of this diamond flat culate. So now they have toroid diamond anvil kind of culate. where on the diamonds, they have a toroid shape of this double well kind of shape. So using this, so how do they make this kind of toroid anvil shape? So this kind of toroid anvil shape are especially made, are especially fabricated using the FIBs or focused ion beam machines. So in the next few slides, I will tell you detail about these things. Like this is a typical diamond, toroid diamond anvil. So you see here in the central part, this is a final culet size, and this is a dip, and this is again a second culet or second shape, anvil shape of toroid. And this one here is the gasket inside the toroid anvil. So this is the sample assembly, and this you see the special shape of toroid anvil. So this gasket takes a special kind of shape because of toroidal shape of your diamonds. And this is one particular photo. So here we are not using the double stage anvil. We are using the same kind of diamond, but we are changing the profile of the culet. We are changing the profile of the culet in terms of a toroid. So with toroid, what happens? It makes it possible to do all those kind of experiments which are possible using the normal diamonds or normal or bevel culet diamonds. So this is a typical sample chamber loaded with aluminum sample. Here you see, and in the toroid anvil, so you can see the transparency from the aluminum. Like there are some portion which are still the pressure transmitting medium, because of which you can see the transmittance through the sample chamber. And the advantage of this kind of anvil cell is this works like a standard diamond anvil cell. So you see here a scan through the X-ray of X-ray absorption and another scan through the profilometer. So you see this dash line shows your normal culet of around 40 micron, and when you make a toroid anvil shape with the central culet of 16 micron and this D2 is 60 micron. So the flat portion is 60 micron, and then the further flat portion is 80 micron. So using this kind of particular geometry, where the central flat is 16 micron, second flat is 60 micron, these people like Diwale and all, they have claimed the pressure of 600 GPa using this kind of cell. And so here you see this diagram. So using this cell, they have increased the pressure using the membranes. I think Dr. Himanshu might have explained to you guys like how you can use the membranes to increase the pressure. So to exert the forces or to bring the anvils closer, you can have different kind of force applying mechanism based on lever arm or based on screw or nut based or based on membranes. So they have plotted this pressure achieved versus the membrane pressure. So they have divided into 3 stages: stage 1, stage 2, and stage 3. So you see in stage 1, the pressure is increased slowly. In a stage 2, it is almost linear increase, and stage 3, it then saturates actually. And this inside shows the equipressure diagram for this sample chamber in the -10 to 10, like 20 micron sample chamber. And this again shows the thickness, gasket thickness versus the distance in the whole culet, flat culet the 400 micron range. So you see here the special shape because of this toroidal gasket. So because of this special toroidal shape, the pinching of the gasket is really can be avoided. Not only pinching can be avoided, it also helps in doing many experiments like resistance measurement and all those things. So it helps in laying down the electrical leads very meticulously, and even at very high pressures, you may be able to avoid the pinching of those leads. So this thickness of the rhenium gasket, they have measured using X-rays of 0.37 angstrom. So this is almost close to more than 40 keV X-rays. So that's the advantage of synchrotron having higher flux, that you can use really very high energy X-rays to probe these kind of studies or these kind of cells. So what they have done, they have studied gold inside the rhenium gasket. So these different patterns, they show the gold inside the rhenium gasket. So this is a diffraction pattern at 409 GPa, and this is a diffraction pattern at 603 GPa of gold inside the rhenium gasket. And this is the equation of state of gold, which they have derived based on these experiments. And this is a typical at 450 GPa even, you see how the sample cell looks like. This is all because of this toroid anvil cell. Otherwise, at with the beveled anvil or double staged anvil, your pictures, your optical micrograph pictures are really not so good. You like I described the bulging effect. Because of those lensing and bulging effect, you will not be able to see these kind of pictures or this kind of optical micrographs. So they have determined the equation of state of gold up to 600 GPa experimentally using this kind of toroid diamond anvil cell. So this kind of diamond anvil cell, these devices have the advantage.
I guess Ajay,
Yes,
is already 5:15. I think it's about the time we should stop.
Okay, then I will stop here maybe. And from the next slide onward, maybe I will.
Yeah, you can repeat if some part, if you think for continuity it is needed.
Yeah, this slide only. Next it is, so advantages of t-DAC is, like in these devices, you really keep the asset of diamond anvil cell intact. So you can use many lab-based experiments using these kind of diamond anvil cells, and these are reproducible and very similar to the conventional diamond anvil cells. And even you can accurately characterize solids to all kind of samples like gases using these cells. And even you can record Raman signals from the diamond anvil, and XRD from rhenium gasket can allow the independent measurement of pressure. So in a nutshell, like we have this plethora of diamond anvil cell, starting from the flat culate with the larger size, like typical sizes are 300 micron to 400 micron. And then we graduate to the culate with the bevel, like single bevel. And then we further graduate to the culate with the double bevel. And with the using this single bevel and double bevel culate, the limitation of the pressure range is you can only go up to like 350 or 400 GPa. So if you want to go really beyond that, you necessarily need to go for the different concepts, like either using the double stage anvils or the toroidal kind of anvils. So from here onwards, maybe I will delve into next lecture, detail about the pressure calibration techniques at megabar pressures. And in the next lectures, I will also talk about the high pressure and high temperature and advantages of those and experiments and examples. Thank you.
Are there some questions? Were there some questions even in your previous talk?
I don't think so.
Okay.
Is there any? No.
Now, once you go offline, I may like to talk to you for a moment.
Yes, sir.
So let me know when you're okay. Can you hear me? Hello? Hello?